Swayam Prabha. Digital India. Educated India.
Welcome to the lecture of Ionic Polymerization. And if you recall that in the previous lectures we discussed about the concept of propagation, then we discussed about the chain transfer and termination in the second lecture of this ionic polymerization. Then we developed the various kinetic equations for this cationic polymerization. And in this particular chapter or in this lecture we will discuss about the validity of those steady state assumptions being taken care in due course of time. Then we will discuss about the absolute rate constants. We will analyze the effect of various reaction mediums. We will discuss about the energetics and anionic polymerization of carbon-carbon double bond. We will try to develop a distinguishment between the radical cationic and anionic polymerizations, or among radical cationic and anionic polymerization. So let us start with the first thing, that is the validity of steady state assumption. Now during the course of the kinetic study we need to take various assumptions to generate the various kinetic equations. Now when we talk about those developed equation, then we need to check the validity of those assumptions being taken during the course of development of those equations. So in this category, the equations which we had developed, we have taken the assumption of a steady state. Now the assumption of a steady state for this ym plus iz minus is not valid in many cases. So before we proceed further, let us look around that what are those cases. Now the cationic polymerization reactions which proceed so rapidly that sometimes these steady state is not achieved or not achievable. And in slower polymerization, where usually when Ra is greater than Rt, so as the concentration of propagating centers slowly increases throughout, the polymerization reaching to a maximum late in the reaction, and therefore and then subsequently it has a tendency to decrease. The existence of a steady state, this can be ascertained by measuring this ym plus iz minus complex as a function of time. Now since this is relatively difficult in most systems, it is more convenient to observe the polymerization rate as a function of time. Now this steady state is usually implied if the rate of propagation is constant with conversion, except for the changes due to the decrease monomer and initiator concentration. Now sometimes a more rapid declination in the rate of propagation with time may be observed, that indicated by the decrease in the either monomer concentration or Zy concentration. This signifies the non-steady state condition. Now in the absence of steady state would also be indicated by an increase of rate of propagation with time. Now let us have a look about the absolute rate constant, because this is again a very important concept when we talk about the kinetics. So the degree of polymerization under various reaction conditions is used to obtain in the Kt upon Kp, the Kts upon Kp, then Trm upon Kp, or sometimes referred as Cm, and Ktrs upon Kp, that is sometimes referred as Cs. That is a ratio which we developed in the previous lectures, equation number 12. Now these experiments may varying with respect to the concentration of monomer in the absence of chain transfer agent. This may yield a linear plot of 1 upon bar xn versus 1 upon concentration of monomer, and in that case we may obtain the intercept which is equal to Cm, and the slope of that particular plot is given by Kt upon Kp plus Kts upon Kp. Now the two ratios, these can be separated from each other by chemical analysis of polymer end group. So there are various tools available as on date through which you can perform those analysis to assess what kind of polymer end groups, what is the concentration of those polymer groups are present in the reaction mass. Now, spontaneous termination and chain transfer to monomer both yield the polymers with unsaturated end groups. So, while combination with the counter ion yields polymer end groups, they derived from the counter ion. The end group analysis combined with the calculated value of either Cm or Kt upon Kp plus Kts upon Kp, this allow the separation of latter two ratios. The value of Cs is usually obtained by carrying out experiments with varying amount of chain transfer agent. So, you cannot nullify the importance of those experiments which are essential part of these polymerization process. If we talk about the plot of the data which contains the information pertaining to this equation, that is 1 upon bar xn is equal to 1 upon xn bar at start plus Cs, that is the concentration, upon m. You may refer as this equation number 18 in continuation with the previous lecture. Now, as the 1 upon xn versus s upon m is a linear, that the slope may be represented by this Cs upon 1 upon bar x naught. The value of 1 upon x and bar in the absence of chain transfer agent is usually given by the sum of first three terms of the equation which we represented in equation number 12. Now, let us have a look, because when we talk about the validity, then again these validity concept is usually supplemented by the experimental determination. So, the experimental determination, when we talk about this experimental determination, this one involves the short stopping of polymerization system by addition of a high efficient terminating agent. Now, so all propagating centers are sometimes quickly terminated with incorporation into the polymer of an end group derived from the terminating agent. Now, those end group in the polymer, they are analyzed after separation of the polymer from the other components in the reaction system, and that is quite obvious because there are usual experimental methods through which you can analyze, and you can analyze the concentration. You can find it out that what kind of different polymers are being formed during the course of the reaction within the reaction system. Now, this particular method is limited by the general difficulty of end group analysis, since the concentration of end group can be quite low, and by the need to assume the terminating agent terminates all kind of propagating centers. Now, second aspect in this particular approach is that is attributed for the determining the propagating species concentration. This involves a direct UV visible spectroscopic analysis of propagating species during the polymerization. Now, the high extinction coefficient of some aromatic carbocations propagating species, they are coupled with the availability of higher accurate spectrophotometers. They are resulted in the extensive use of that particular method, and it is very common technique for analysis or for experimental determination. Now, the measurement of UV absorbance of a polymerizing system as a function of time, this allows one to determine the Ki, that is the rate constant for initiator, then Ri, that is the rate of initiation step, the concentration of propagating species, and the rate constant of the propagating reaction. Now the UV method, this is also being used to study very fast polymerization. Now sometimes in stopped flow or a rapid scan spectroscopies are also feasible. Now this separate monomer and initiator solution with the help of a rapid force through a mixing chamber where the instantaneous mixing usually occurs, and then it is subjected to a capillary tube located in the spectrophotometer. Then the flow is stopped and the progress of reaction being followed by measuring the change in the absorbance with time. Another new method is referred as the diffusion clock method. This offers an alternate approach to obtain the propagation rate constant. Now usually this involves the polymerization in the presence of an highly active terminating agent. Now these are specifically known to have a high rate constant for reaction with the carbocations at the diffusion controlled reaction limit, and sometimes these limits are in the range of 3 into 10 to the power 9 liter per mole per second. Now the ratio of the rate constant for the propagation to that for termination is obtained from the measurement of the amounts of monomer and the terminating agent whatever being consumed due course of a reaction system. Now these ratios are or this ratio multiplied by the diffusion controlled reaction rate constant K yields the propagation rate constant. Now sometimes you need to incorporate the various corrections in calculating the rate constants. Now these corrections are attributed to the kinetic expressions, those who are written in terms of only one type of propagating species and usually shown as ionic pair. Now usually this is incorrect since both ionic pairs and free ions are simultaneously present in most polymerization system, and sometimes they are in the equilibrium with each other. Therefore, the correct expression for the rate of any step, initiation, propagation, termination, transfer. So, the rate of any step in the polymerization should include the separate terms for respective contributions of the two type of propagating species. For example, the propagation rate should be written as this Rp is equal to Kp plus Ym plus m concentration of monomer plus Kp plus Ym plus Iz negatively charged, then the concentration of monomer. Now where this Ym plus and Ym plus Iz which we are referring, they are the concentration of free ions and ionic pairs. So by this way we are having the combination of both the things or both important things in the reaction mass. So most reported the rate constant for propagation values are only apparent or pseudo or a global rate constant. So the Kp apparent obtained from the polymerization rate using the expression. So Rp sometimes this mathematically be represented as Rp is equal to Kp apparent into the concentration of monomer star m star into m. Now this m star is the total concentration of both type of propagating species. Now the apparent rate constant is not really a rate constant but a combination of rate constants and concentration. So the mathematically it can be represented like this, that is the K apparent, that is Kp plus Ym plus Kp bar plus minus Ym plus Iz in minus upon K Ym plus Ym plus Iz negatively charged. Now there are two approaches to separate the Kp apparent into the individual Kp plus and Kp plus minus values. Now one approach involves the experimental determination of the individual concentration of free ions and ion pair by a combination of conductivity with the short stop experiment or UV visible spectroscopy. Now, conductivity directly yields the concentration of free ions, that is only free ion conduct short stop experiment. Now, these short stop experiment yield the total of ion pair and free ion concentrations. So, it may have the combination of both. Now, UV visible spectroscopy for those monomer, sometimes these monomers are aromatic in nature. So, these where it is applicable, this also used to obtain the total of free ion and ion pair concentrations. Now, it usually assumed that ion pair, they show the same UV visible absorption as free ion, since the ion pair in cationic systems are loose ion pair, that is attributed to the large size of negative counter ions. Now, this approach is limited by assumptions and or sometimes or experimental difficulties inherent in the various measurements. Now, there are several experimental difficulties may be attributed to the irreversibilities associated with those experimental procedures. So, it is quite obvious. Now, the conductivity measurements on systems those containing the low concentration of iron are difficult to perform, and impurities can easily lead to the error in the results. Now, the short stop experiment do not distinguish between ion pairs and free ions. The assumption of the equivalence of free ions and ionic pairs in the spectroscopic method is usually or you can say not firmly established. So, the second approach, this involves the determination of polymerization rate at various concentrations of co-initiator and initiator, or in both the presence or absence of an added common ion salt. So, we discussed various salts in due course of time. Now, this latter containing the counter ion of the propagating carbocation, this actuates the propagation by ion pairs by depressing their ionization to free ions. Now, let us talk about in brief about the effect of reaction media, because reaction media again play a very vital role in deciding the fate of these polymerization process. So, the change in the rate of polymerization sometimes can occur when the solvent or counter ions are changed, because both of them are act as a reaction media. So, it can affect as the equilibrium between the free ion and ionic pairs that may be shifted towards the free ions by high polarity solvent. This usually result in the increased polymerization rate. Now, the large solvent effects, they can be seen for the system in which the counter ion has a significant tendency to form a covalent bond to the carbocation. Now, sometimes low polarity solvent plays a vital role. Now, these low polarity solvent drive the reaction system towards the covalent species I, which does not propagate or at most propagates much more slowly than does the free ion or ionic pair. Then let us talk about some energetics within this particular polymerization scheme. Now, the cationic polymerization, they are usually exothermic in nature, since the reaction involves the conversion of pi bond to s bond. The heat of polymerization of for any particular that we need to look into. Now, the monomer is essentially the same irrespective of the mode of initiation. So, these are the couple of points which we need to look into when we talk about the energetics. The composite activation energies sometimes play a very vital role, and these are ER and XN. These are the activation energies for initiation, propagation, and the termination. So, the composite activation energy, that is ER and E bar XN, they are referred as ER is equal to EI plus EP minus ET, because termination is some sort of desired effect. Then E bar Xn is equal to EP minus ET. So, where this EI, EP and ET are the activation energy for the initiation, propagation, chain termination steps. Sometimes we may ask for the activation energy. For the activation energy for Xn, the ET will be replaced by E termination term, or term when this transfer transfer terms occur. So, ETR represents the transfer terms. Now, let us talk about the anionic polymerization of the carbon-carbon double bond. Now, because previously we discussed about the cationic polymerization of carbon-carbon bond, now in the same line we will discuss about this carbon-carbon double bond concept under the edges of anionic polymerization. The propagating species are anionic ion pairs and free ions with a relative concentration that depend on the reaction media, as we discussed in the cationic polymerization. Now, unlike cationic polymerization, there is a large difference between the reactivities of ionic pair and free ions in anionic polymerization. Although anionic polymerization then generally proceeds rapidly at a very low temperature, so they are seldom as temperature sensitive as cationic polymerization. So, you will see that we are differentiating between these anionic polymerization and cationic polymerization under the edges of carbon-carbon double bond. So, they are having a very minute, or you can say not much difference between these two polymerization schemes. Now, most anionic polymerization possesses positive ER values and proceed well at you can say, or somewhat above ambient temperatures, and many anionic polymerizations are easier to understand, since the identities of initiating species and counter ion are much better established in this case. The range of solvents useful for the anionic polymerization is usually limited to aliphatic and aromatic hydrocarbons and ethers. Sometimes people may consider the halogenated solvents. So, halogenated solvents, they are suitable for cationic polymerization, cannot be used for anionic polymerization because their facile nucleophilic substitution reaction with the carbon ions. So, other polar solvents such as esters, ketones, they are also excluded in the anionic polymerization as a result or as an because of their affinity under the reaction with the carbon ions. Termination usually occurs by transfer of a positive fragments, usually a proton, from the solvent or from some other transfer agent, both deliberately added. Although other modes of termination can also be occur during this anionic polymerization step. Now, many anionic polymerizations are living polymerization when the reaction components are appropriately chosen. So, now at the last when we discuss about, because we have discussed the radical polymerization, we discussed the cationic polymerization, we discussed anionic polymerization in brief. So, let us have a distinguishment or distinguishing between the radical cationic among radical cationic and anionic polymerization. There is a common question that as to whether a particular initiator or initiator system initiates polymerization by radical, cationic or anionic means. Such a question can easily arise for various examples. For example, in polymerization initiated by ionizing radiation, the mode of initiation of a particular initiator can be distinguished by a consideration of its characteristics compared to those of known radical, cationic and anionic initiators. So, we have enlisted a couple of things related to this distinguishing factor. The ionic polymerization usually proceeds at a lower temperature than the radical polymerization. Although the ionic reaction temperature are usually below 0 degrees Celsius, there are numerous ionic polymerization that proceeds at higher temperature, but their rate is a bit lower compared to those who are happening at below 0 degrees Celsius. Radical polymerization on the other hand almost, or you can say always, proceeds at a temperature appreciably above approximately 50 degrees Celsius. Further, the ionic polymerization invariably have lower activation energy than the radical counterparts. In some cases, there may be actually possess negative activation energy. So, that is the point to be addressed, and that is a very important point. Another part is that the ionic polymerizations are distinguished by their marked sensitivity towards the change in the polarity and the solvating ability of the reaction media and counter ion effects. Usually radical polymerization, they do not show such kind of effects. The next part is that the addition of known radical scavengers like DPPH radical in the polymerizing system with the hard polymerization if it is a radical reaction. Now, ionic polymerizations will be unaffected by such kind of additions. One thing very important, that one must be very careful, however, not to use the radical scavengers that also affects the ionic polymerization. Therefore, the benzoquinone would be a poor choice as a radical scavenger, since it can also act as an inhibitor to ionic polymerization. So, the feasibility of these type of compounds need to be addressed prior to use in any kind of a polymerization system. Another part, that is the chain transfer constant for an additive or solvent in the polymerization, it can be determined. Now, this value can be compared with the transfer of constants for the same substance in the polymerization of the same monomer by known radical, cationic or anionic initiators. So, in this particular chapter, we discuss the remaining part of anionic polymerization. Then we discussed about the various aspects of the cationic polymerization steps. Then we discussed the distinguishment among radical, cationic and anionic polymerization. Again, we took the reference from this particular source, and for further studies usually promoted if you are interested, and you can seek the help of these references which are enlisted in this particular slide. Thank you very much.